Okay, we are here now and at the cusp of what I hope will be our final result of this analysis of the finite element method. So this is best titled Convergence of the finite element solution. Okay, before I state the result and prove it, there's one result that I need to recall from a few segments ago and generalize it. Okay, so recall that when we actually started talking about the analysis of the method, we used this, or I stated the fact that the H1 norm is equivalent to the energy norm. Okay, so recall equivalence of H1 and energy norms. Right? And the way we stated that result is the following. We said that if we look at C1 times the 1 norm of V, right, some function V, this is lesser than or equal to the energy norm of V. Well, this is actually the energy norm squared, so we do that. Okay, and it's also less, it can be bounded from above by the energy norm, and the energy norm itself can be bounded from above by some other constant multiplying the V1 norm. Right, and I believe there was also a question about what exactly we meant by this equivalence and how it held, why it might hold, and I said that, well, it really rests crucially upon the fact that when we speak of these norms, we are talking of quantities that are real and therefore bounded, they're not infinite. And then using the fact that our domains are finite, we can actually prove this result. Okay, so so we have this. Now it emerges that this equivalence between the H norm and the energy norm extends, in fact, to the general Hn norm also. Okay, so this extends to the Hn norm. Right? So this says that if we just look at C1 times the n norm of V, it is bounded from above by the energy norm. And that itself can be bounded from above by some other constant multiplying the n norm of V. Okay? And the reasons why this holds are pretty much the same why the H1 norm holds, why the result holds for the H1 norm. Okay? So this is what we're going to use. All right, so here is our statement. Again, I'll state it as a theorem. The theorem is one on the n norm of the finite element error. Okay, and it states that it can be bounded from above by some constant, whatever constant, some constant, right? Let's denote this constant as C bar. He, again, raised to the power of alpha, where alpha is the same exponent that we came upon in our Sobolev interpolation error estimate. Okay, this times the R norm of U. Okay, so this looks very similar to what we saw for the Sobolev error estimate, except that now we are indeed talking of the finite element error estimate. Okay, we are indeed talking of what happens with the finite element error, right? And we just remember that this is UH minus U. Okay, all right, proof. And let me just start, well, I could start the proof here. And to start the proof, let us actually start with this result I've just stated at the beginning of the segment, the result just above the theorem, right? And let us start by writing C1 times energy norm, sorry, N norm of finite element error. Using the result we've just stated above, it is clear that that can be written as being bounded by the energy norm of the error. Okay? All right. Now, let's move on. Okay, I'm actually going to reproduce this last statement on the new slide here. C1 N norm of the finite element error is lesser than or equal to energy norm of the error. Okay? Now, the energy norm of the error itself, you recall from a couple of segments ago, is bounded by a quantity which is also the energy norm of UH minus U. Right? We call this the best approximation property. Right? This is the best approximation property. Okay? Now, I want to state something about notation here when one is working with inequalities. When one is working with inequalities and I write inequalities running in this fashion, the way to read it is that what we have here, the energy norm of E, is greater than or equal to C1 times the N norm of E. When we come down to the second line, what we are seeing is that what we wrote on the first line is itself less than what we wrote upon this on the second line. So it's very similar to actually taking what we have on the second line here and moving it back here. Okay? That's how we understand these. That's the notation that's used when one is writing on multiple lines. Okay? So what this is stating is in fact the best approximation property, right? Because there we did indeed prove that the energy norm of the error is lesser than or equal to the energy norm of this particular quantity. Okay? But now note that when we chose those functions UH, okay, included in those functions was this interpolate U tilde. Because UH, after all, was just functions living in SH, right, and satisfying the Dirichlet boundary condition. Since U tilde H also lives in SH and is in fact equal to the exact solution at the nodes, it also does satisfy the Dirichlet conditions, right? So it is in fact one of these members, right? So the reason we get this result is the best approximation property and the fact that U tilde H also belongs to SH. Okay? All right. But now one can again invoke the result I stated at the before we started this theorem, right, on the equivalence of the energy norm and the N norm. So we can say that that energy norm that we have on the right hand side itself is lesser than or equal to, let me see this, right, I could directly write this as some other constant C2, right, times the N norm of u tilde h minus u. Okay, just from the fact of our statement on equivalence of norms. Okay, all right. So we have this, and what we can do now is invoke. So this result follows from equivalence of Hn and energy norms. Okay. Now, continuing to work, we recall our Sobolev interpolation error estimate. Okay. So that interpolation error estimate is one that is applied to u tilde h minus u, right? Because that's the interpolation error. Okay. And that was that u tilde h minus u is lesser than or equal to some constant c he to the power alpha times the R norm of our exact solution. Okay, so this is the Sobolev interpolation error estimate. Okay. All right, but now look at where we've got. We started out with C1 times the n norm of our finite element error, and through this process, right, of repeatedly invoking various results that we've accumulated, we have arrived at the fact that it is bounded from above by the term on the right hand side. So let me now just collect these results to say that the n norm of the finite element error is lesser than or equal to C2, which is a constant, times C, which is a constant, and divided by C1, which is yet another constant, times HE to the power alpha. Okay. Now this is our new constant C bar. Okay. So our final result is that the finite element error in the n norm is lesser than or equal to C bar, which is a constant, HE to the power alpha times the R norm of u. Okay, that's our result. Now, let's just spend a couple of minutes examining this result. Okay, what it tells us is that again, you know, if we look at cases where the solution is the exact solution is very smooth for u sufficiently smooth, what we're seeing is that alpha, which is defined as the minimum of k plus 1 minus m and o. Okay, in this case, we're working with the n norm, right? So we have k plus 1 minus n. I'm sorry. Okay, and r minus n. Okay, so alpha is the minimum of those two quantities, right? So for u being sufficiently smooth, what we see is that alpha is indeed equal to k plus 1 minus n, right? Where k is the polynomial order of our basis functions. Right, and n is really the number of derivatives that we are taking in calculating the norm of the error. Okay, All right, to get a little more insight, let's consider what happens with, let's consider special cases, right? Consider n equals 1. So we're considering the 1 norm, right? The H1 norm. And, well, let's just consider n equals 1. Okay? In this case, our result becomes that the H1 norm of the error, what do we mean by the H1 norm of the error? What we're saying is we're looking at the error in the finite element solution, square integrating it, and also square integrating the derivative of the error. So we're trying to gain control not only over the error, but also its derivative. And we're demanding that the error be somewhat smooth, because we want to say that even its derivatives should not get very big. Okay? So we're not only saying that the error shouldn't be too much, but it should also be smooth, right? Okay. So this thing now is lesser than or equal to our constant C bar, HE, okay, to the power k plus 1 minus 1 times the R norm of U. Okay? So it is saying that if we are looking at the H1 norm of the error, basically we're trying to look at the error itself and its derivative, right? It converges at the rate of k, right, our polynomial order, right? So for linear basis functions, right, for k equals 1, okay, we get the error in the 1 norm is essentially proportional, right, to, well, let me not say proportional. The error in the 1 norm of the error is bounded by C bar HE. So indeed, as we refine our mesh, HE goes to 0, right? As HE tends to 0, the 1 norm of the error will also tend towards 0. Okay? But note now that if we were to go to higher polynomials, right, the same 1 norm of the error would now converge at a higher rate. Okay? All right? Okay. Now, so this is the main sort of result that we wanted to establish. And of course, as we go to higher and higher order polynomials, our error converges more rapidly. Now, if we want to compute the error in the L2 norm, right, which is equivalent to the H0 norm, there is an additional technique that needs to be invoked. It's called the Aubin-Nici method, which we won't do because that takes a lot more work. Okay, but essentially in this setting, the result is the following. If we consider the L2 error, right, and I'll make it explicit that we're talking about the L2 error. Now we're just talking about square integrating the error, right? No derivatives. Then the form is essentially the same. Okay? In this case, we get h to the power k plus 1, no derivatives, right? So we don't lose any powers here. We don't have k plus 1 minus n, okay? Times the R norm of the exact solution. Note that, of course, we're assuming that the exact solution is sufficiently smooth so that that exponent alpha always reduces to k plus 1, right? So this is the condition for the L2 error. So what this means now is that with k equals 1, the L2 error of our finite element solution converges quadratically, right? It converges at HE to the power 2, right? And so on, right? So if we had k equals 2, we would converge at the rate HE to the power 3. And so on. Okay? So essentially, this summarizes the key result that is used in conventional finite element error analysis. It says that as we refine the mesh, our solution converges, right? And depending upon the measure of error we want to use, either just the L2 norm of the error, which would be just square integrating the error and making sure that that quantity is decreasing, okay? Or whether we want to include higher order derivatives of the error, we can address all those problems. Okay, we can address all those questions. In all of this, at least in the way I try to bring out to give you greater insight into what is happening, we're assuming that the exact solution itself is smooth enough. And note that this is a requirement. If you start out with trying to solve a problem whose exact solution itself is very very irregular, you can't hope to converge to solutions easily, right? It just becomes much more difficult. There are methods that can be used to address such problems and also to carry out the error analysis of these methods. The other thing I should note is that the interest in compute in always looking at errors which involve an integral over the domain is precisely to make sure that we are actually controlling the error all over the domain. Okay, and this is why we always take either the square integral of the error itself squared and integrated, or we compute a further derivative on it and square and integrate that. Right? The whole reason for integrating it is to make sure that we have control over the error over the entire domain. Okay, this is a good place to end this segment.